Good morning, everyone. Today we are going to simulate and study the impact of intermodal dispersion in multimode step index fiber and multimode graded index fiber and prepare a comparative study. So here first we will be defining and writing the expression of intermodal dispersion for both multimode step index fiber and multimode graded index fiber, and then prepare a comparative study of the dispersion for both the cases. The equations that we have to simulate for intermodal dispersion on a multimode step index fiber is the pulse broadening sigma is ln1 delta by 4 root 3c, and pulse broadening for a multimode graded index fiber is sigma. So for this, the only three inputs that we require is ln1 and delta. C is a constant. So I'll go to our lab view window and select these input terminals. Now first we will select our input terminal, the length of the link in kilometer, then refractive index of the core, then relative refractive index, difference, a counter, input power, and the attenuation in dB per kilometer. We'll again go to the properties and make the digital display for all the values for the convenience of setting the values. Now to see the output, pulse broadening in step index and graded index fiber, we'll be selecting the gauge. For similarly, we'll be selecting the gauge for the pulse broadening of graded index fiber in nanosecond. Now to see the output, we will be using the extended XY graph for step index fiber and for the graded index fiber. Now we will be making our block diagram. The first thing that we'll be doing is selecting the for loop, as you know, for making the. Now again we'll be using the formula boards for calculating the pulse broadening of step index fiber and the graded index fiber. So for the step index fiber, the first thing that we need is the link length, the refractive index of the core, and the relative refractive index. Now the pulse broadening is L into N1 into delta divided by 4 into square root of 3 into C, which is 3 into 10 to power of 5 kilometers per second. We are taking in kilometers per second because our length is also in kilometer. Press OK. Now connect the input terminals with the values on the formula board. Now we have the sigma. Now to calculate the power output, we know the formula for it is. Again, we'll be using to calculate the output power. Again, we'll be using the formula board. And we know the value is, we need the link length and attenuation alpha, and the value is 10 to power of minus alpha L by 10 into Pi. So I'll give one input terminal the input power, so that will help us to calculate the input power. So this will give us the value of input power. Now connecting the values on the formula board to the input terminals. The product of the Gaussian term and the output power will give us the output Now this pulse broadening that we are getting the unit is in seconds. We need to convert it into nanoseconds. So first what we will do is we will first multiply the value with 10 to power of 9. Now we have the pulse broadening in sigma s and the output power, but we know to get the pulse we need to multiply it with the Gaussian term. So again we'll be using one formula board to calculate the Gaussian term. So the first term will be x and the other is sigma. So it is e to the power of minus x square divided by 2 into sigma square. Now we'll be connecting x to our counter, which will set to x minus n by 2, where n is the counter. For that we need to divide the counter by 2. Now connecting this x to formula board 3, sigma sigma will be connected to the value of sigma. Now this Gaussian term is to be multiplied with the output power to get the power for the output pulse. So we need a multiplier. We can connect the Gaussian term to one leg and the output power to the second leg, and connect the output to the Y terminal and X to the counter and set the reset to false. Similarly, we need to repeat the same thing for the graded index fiber by selecting a formula board for calculating the sigma. It is N N1 now we'll make the connection. Again, this pulse width is in seconds. We need to convert it into nanoseconds. For that, we need a multiplier. One on the other leg, create a constant and enter the value 10 to the power of 9. Now at this point, we will be connecting our gauge to measure the pulse broadening. This we need to use it for making the Gaussian pulse, for which again we will be using the formula board. So the Gaussian pulse is e to the power of minus x square divided by 2 sigma square. Okay. Now we'll connect the inputs. So sigma and x to the counter. The result is to be first multiplied with the output power. So we need a multiplier. And this needs to be fed to the y terminal of the xy graph. And x needs to be fed to the counter. And reset should be set at false. Our circuit is complete. We can run it and see it. We can simply just set our values. Once we set our value, we can run and see, and it clearly shows that you have a broader. This is because of the modes traveling through different path lengths reach the destination at a different time, resulting in more pulse broadening in step index fiber, which is compensated in graded index fiber because in graded index fibers, different modes with different path length travel through the material with different refractive index and hence have a different velocity. And hence both reach the destination at the same time, which results in small spectral broadening. Thank you.